Okay, hi everyone. My name is Javed Ahmadli, and this is my presentation for homework exercise 1 for computer organization and architecture. The topic of this assignment is looping without branching. In this project, I'll demonstrate how to implement a loop in ARM32 assembly without using any B or B condition instructions, only using move PC to some kind of register to control program flow. So let's take a look at the problem statement. So normally in ARM assembly, we use branch instructions like B or BGT, BLE to jump back to a loop or move to another part of code, like an else statement, for example. However, in this homework, the rule was very specific. No B or B conditional instructions. Instead, we must manually modify the program counter or the PC to jump around the code. Essentially, we're simulating branching manually by moving the PC to some kind of address that we've calculated manually by ourselves. So our goal, so our goal is to, basically the purpose of this assignment is to compute the sum of all integers from m to n using a loop. So if m equals 1 and n equals 10, for example, the final result should be 55. The logic is simple in C or Python, just a while loop adding numbers. But here we're writing it all in assembly without using branch instructions. Let's take a look at the algorithm. So we start with a value of m in register R0 and n in R1. We won't be using memory access, so we're going to add the values ourselves. And we're going to also initialize an R2 to 0, which and this register will hold the sum of of all the numbers between the two uh, values. And while R0 is less than R1, we're going to add R0 to R2 like an accumulator and increase R0 by 1. When R0 reaches N, stop and execute SVC2, which is basically a supervisor call which calls to stop the function or end the program. In short, we are recreating a loop without using the branch instruction. That's it. So, so what are these registers? What are they assigned to and what are their roles? R0 and R1, we've looked at those. They are R0 is the starting number, for example, 1, and R1 is the goal state, which is 10, for example. And R2 would be our accumulator, to which we'll add our zero values incrementally until we reach the value of the sum of all the values between 10, 1, and 10 with 1 and 10 included. And R3 is basically our reference for uh, our reference for bytes per instruction word. So basically every instruction word that we have has a is 4 bytes long. So we store a value of R3, which we're going to use later in the program, and I'll explain how we use it. And and we have the register 4, which will store the offset or how far back to jump, and I'm going to show that as well. And R5, which will store our actual computed address, which we're going to branch to. Okay, so before we jump back, jump before we jump to the code, I'd like to explain how PC manipulation actually works. So in ARM32, at least, the program counter doesn't actually hold the exact address of the current instruction. For example, we are in a particular code here, right? So if we're going to add the address of the PC counter to register here, it won't be the address of this current instruction. It will be the instruction of this address, but 2 steps ahead, like 8 bytes ahead. So it's going to be the address of this instruction plus 8. And we're going to consider that when we manually compute the bytes offsets for our branching. Okay, so that's an important thing I want to point out. Now, let's quickly go through the code and see how it works. So first of all, I'd like to show you how this works with branching. It's a pretty easy code. So we have R0, R0, R1, our accumulator, and then we're going to compare. If it's greater than, we're going to move to both, which is going to call the supervisor call. And the loop is easy. We're going to add R2, R0 to R2 and increment R0. That's it. We're going to loop back. However, due to many reasons, uh, we have to remove the loops. Uh, could be due to performance reason, most definitely. In loops, it's always better to avoid branching at all costs. So let's see how we do this. So first we can remove the loop branch, the B loop. How we do it is we can move R5 to PC, and what this does is, as I said, it's going to move the value of the current instruction plus 8. So we have that, and then we calculate here is the value for offset. I haven't used R3s or R4 registers yet. I just calculated the offset here. So this is going to move -24 divided by 4. This is going to move 6 steps back. So when we do move PC to R5, this is going to move 6 steps back. So 1, 2, 3, 4, 5, 6. It's going back to the start of the loop. Now, how would this how would this look like when we remove all kinds of branching, and we only use uh, this uh, type of this move PC to our to particular register instruction. And that's how this is how the full code looks like. So we have our R0, we have our R1 value, we have our R2 value, the accumulator, and we have the R3, which is bytes per word. So now let's look at our loop. For our loop, we have a compare function. This compare function is going to check the difference between R0 and R1. So when we start, we're going to compare 1 and 11. So 1 minus 11 is going to give a negative number. It's going to update the NZCV flags, and it's going to show at this at the first case, R0 is smaller than R1. So we're going to move on with the loop. So we're going to add R2 to R0, add R0 to R2. So we're going to add the value of R0 to our accumulator. So R2 is going to be 1, and then we're going to increment R0, and R0 is going to become 2. Now let's move on to the most important part. So what does this do? This is a move less than, so this is a conditional move instruction. So what is the condition? So if the compare value, so if R0 is less than R1, we're going to move a value. What is this value? -7. So why are we moving -7 to R4? What this value, R4, is going to dictate the offset, so the number of instructions or steps we need to take back. So we need to take steps back to branch back to loop. So here I put a value of 7, so that means we're going to move back 7 instructions in the code. And we need to do a multiplication. Why? Because each instruction costs 4 bytes, so we need to move 4 bytes each. So we're going to multiply -7 by 4, which is going to give us -28, which will allow us to move which will later allow us to move 7 steps back, as we can see here. So we first move R5, we first move the value of the program counter to R5, which is going to be the value of the current instruction plus 8. So we have that, and now to R5 we add our offset. We add our offset, but it is basically a subtraction. So we subtract the value of instructions we need to go back. So if this is instruction whatever, so we're going to move 8 steps back. So when is this going to happen? This is going to happen here. So when we do move less than PC to R5, what this does, so basically they're all less than instructions. So what this does, it changes the value of the program counter to the address of R5. So address of R5 is the value of the program counter plus 8 minus 28. So we're going to move 7 steps back. Let's see. So 1, 2, 3, 4, 5, 6, 7. So what basically we're back at our compare function, and this code is going to run again, again until we reach 11, which is going to do one last addition to our accumulator, increment R0, and then we're now that because the compare gives us a 0 value, not a less than, so we're going to skip the conditionals and move straight back to both, which will have our supervisor call to stop the program. Okay, seems pretty straightforward. Now let's see how this actually works. Maybe it doesn't work at all. Let's see. So this is CPU later. This is CPU later, which is an emulator for assembly code. So here we have the same code, and let's compile and load and see what happens here. Okay, so we initialized R0 to 1. Actually, it'll be much easier to show you just like this. So, uh, okay, these are signed decimal values, so it's easier to see what's going on here. R0 will assign the accumulator, assign the value of 4 to R3. Now we do our first compare. Of course, it's going to be less than. We're going to add R2 to R0 to R2, so it's going to increase by 1, and this is also going to increase by 1. And now we're going to move on to our less than conditionals. They're all going to work. So as you can see here, uh, the PC value here was 36. Now, however, the value that we have in R5 is 44. As you can see, it's 8 bytes ahead. So that is why when we do move less than PC to R5, we're going to move 7 steps back, which is going to move us back to compare. And this process is going to continue until R0 is equal to R1. So it's going to add up. Accumulator keeps adding the values of R0. So we keep on adding, keep on looping. Now that the values are equal, this time it should loop again. It should loop again because now we're going to compare. Now we're going to compare 11 by 11, which means it's not less than. We're going to add 11 last time, which is going to be 66. So we have the correct answer right now. Now let's see if we move to both. We should move to the both label. So we're going to skip this, this, and move straight to both, which is going to end our function and prove that this is correct. So we have 12, 11, and the most important thing, our value is 66, which proves that the system is correct. I hope I was able to properly explain to you how uh, how the program counter architecture pipeline actually works. So I wish I was able to explain the logic. I hope I was able to explain the logic clearly and show you one of many ways we can write a loop without using branching, which is going to be very important in the future uh, because branching leads to many problems. We want to avoid it at all costs. Bye.